Assalamualaikum and good afternoon. We continue. Okay.
Alaikum salam.
So we continue our discussion about boundary layer. So in this discussion is actually previously we know that we have a few velocity distribution. One is linear, quadratic by the power of 3, 4, and 5. 4 sinusoidal. So we have the sine theta as sine pi over 2 y over delta, and we have the Blasius solution. So for Blasius solution, we don't have any velocity profile because Blasius will calculate all the velocity for all the let's say for all the molecules there, and then he create tables, and from that tables we solve the problem. So the problem is we need to know whether that velocity distribution is actually can be changed as we like, or that velocity distribution is actually fixed. Mean we do certain derivation and then comes out the velocity distribution. Okay, let's say we have this question. For example, we have a boundary layer like this one. So we have the boundary layer here, and this is the velocity distribution. And then let's say we assume that this velocity distribution is in second order polynomial. So means in by the power of 2. So and then we need to determine what kind of equation that comes out or can be found in this situation. Okay, I just simplified this solution. So when we have second order polynomial, means in our terms we need the biggest power is 2. So we could write the common equation for second order polynomial as u is equal a plus by plus cy square. So and I think this idea is actually you could do by using the Navier-Stokes equation. For example, you take Navier-Stokes equation, then you take the x-axis Navier-Stokes equation, the Cartesian coordinate, and then you could simplify everything according to the steady flow and so on and so forth. And finally, you will have d squared 2 and so on. So and then if you integrate that one, so you could find this term also. I think this term is in some places in chapter 1, 2, or 3, it comes out. So some certain idea of this one. Okay, just to make, I try to simplify it. So mean we try not to use the Navier-Stokes here. So we just use the common idea of boundary layers to simplify, because we want to focus on the solution of boundary layers itself. Okay. So let's say we have the second order polynomial, and it is in general equation we could have it as u equal a plus by plus cy square, and then as you know we have 3 unknown parameter. So mean because we have 3 unknown parameter, we need to prepare 3 equation to solve to find what is the value of a, b, and c, and that 3 equation can be made, can be created by the boundary condition. So mean we need to have 3 boundary condition. Okay. Normally we will take boundary condition, first boundary condition at here, and the second boundary condition at the top here. Normally that we use in chapter 1 to 3. But in boundary layer topics here, we could get an extra boundary condition at point number 2 also. So we could get 2 boundary condition 2 and 3 at the top here. Okay, okay, let's say for boundary condition 1, you could imagine that if y equal to 0, So the velocity is equal to 0. Then you substitute into this general equation, you could find that the A is equal to 0. Now the general equation for the velocity profile can be written as U equal By plus Cy square. So because the A is equal to 0, so means that no need for you to think about an A anymore. So we could conclude that the general equation now is become By plus Cy square. So and then we substitute with the second boundary condition. So means at the top, so we have the boundary condition here. So we have velocity distribution. So at this point, so at y equal to delta, so the u is equal to capital U. So and then we substitute to this equation. So we get so we get this term. So this is our second equation. So and then we use the third equation. So in the third equation here, we need to manipulate the boundary condition. So we say that at y equal to delta, okay, at y equal to delta, the gradient of velocity along the y-axis will become 0 also. So we write as du dy is equal to 0. So how to solve this? We know that from our basic, from our general velocity distribution, u is equal by plus cy square. So and then we could write du dy is equal to b plus 2cy. So means that du dy is equal to 0, means du dy is equal to 0 at y equal to delta, means that we need to substitute the value of delta here, and then we get b is equal to negative 2c delta. So and then we using equation 2 and 3, we do the simultaneous solution. We could get that the calculation here, okay, and then we could define the value of c is equal to minus capital U over delta square. Now we have the terms of c and also terms of b, and finally we could substitute into our general equation, which is by plus cy square, and then we have this one, and then normally we will bring the capital U to the left hand side, and it will become u over u is equal to y over delta minus y over delta square. So that's why every time when you solve problem, if the problem says that the velocity distribution is in quadratic, okay, you may use this equation straightforward, because this is the common velocity. It is the correct velocity profile for the second order polynomials. Okay, so this is I show you the idea how to determine the velocity profile for the second order polynomial. And if you go to my website, I already upload the third assignment. So I ask you to define, to do this one, to prove that the velocity profile for the power of 3, power of 4, third order polynomial, the quartic equation, and also for the sinusoidal. So wait a minute. The assignment will show you about this. I will ask you to do this one actually. Okay, so in this velocity, in this table, so we have a linear and quadratic, the second order. So I show you how to get this second order velocity profile. And in assignment 3, I need you to prove the third order polynomial and also the fourth order polynomial. It's also known as a quartic function. So you need to prove this one, and also to prove this one, and also to prove this one. And then at the same time, please do your basic calculation as I shown previously to get the value of delta, this one, and also the value of CD. That is the assignment for number 3. So, and then you could submit your assignment 3 at the last meeting. So I will submit another assignment 4, later. Okay, so this means the proof for the for our velocity distribution. So we continue a little bit for our lecture here. Okay, not this one. Okay.